Okay, welcome to Astronomy 101. We are going to be doing week 8. Took last week off for the holiday weekend and some hair dyeing. um, we are going to be talking this week about some astronomy, obviously. So, last week we talked about light and how it can behave as both a wave and a particle. Hey, Todd. Remember, light demonstrates some wave behavior where we can treat it like, it has an amplitude, it has frequencies, it has wavelengths, it carries energy. All of that stuff was pretty well understood in kind of how we utilized light and physics from that. However, they discovered that one of these things that we learned is that if you treat it as a wave, you can kind of get yourself in some trouble because you would think that if it is just a wave, the energy that it carries gets higher based on like a higher amplitude. Basically, if you brighten the light. So if you have like a light dimmer or something and you're playing with it and you say, okay, I want the light to be brighter and you make it really bright. If it is just a wave, that brighter light would carry more energy. But what Einstein found with the photoelectric effect is that when you brighten that light, that doesn't change the energy that it's carrying at all. What does change the energy is the frequency of the light. So if you increase the frequency, if you shorten the wavelength and increase the frequency, that kind of carries, red up to blue and then beyond into ultraviolet and all of that. As that frequency increases, that corresponds with the energy. And that really means that we need to treat light like a particle. But it diffracts and does wave-like things. So it screwed everything up. And as Bender from Futurama said, I don't care if you're if light is a wave or a particle, it sure goes down smooth. So now the electromagnetic spectrum I kind of touched on. When we think about light and we think about, increasing frequencies, we typically just stay in that visual spectrum that we're used to, going from red being lower energy, purple being high energy. But remember, even down to radio waves, microwaves, all the way up through, and then infrared, visible light spectrum, and then all the way up to ultraviolet, X-rays, and gamma rays, all of that is technically light. It's just not light that our eyes process. But if, you're a predator, you'll be able to see an infrared, for example. So it's all light, and it all transmits, either emission, reflection, absorption, all of those things behave the same way. They're just different energies and frequencies. Hey, Brad. All right, so the other thing we talked about is matter. We talked about that atomic structure, the Bohr model of the atom, where you have a nucleus made up of protons and neutrons, and then you have electrons orbiting that. The atom can absorb energy, and that bumps the electron up levels, and then when it loses that energy, it falls back down and emits a photon at a specific frequency. We're going to keep talking about that at the beginning of this one. We talked about phases, how you can have matter be solid, liquid, gas, and plasmas, and that it's not just temperature. We typically think about phase transitions as being, if you have ice, cold water will freeze to ice. You heat it up, it turns to a liquid. You heat it up more and it turns into a gas. But you can also affect the phase of matter based on pressure. So even though Mars exists somewhere that, you could have liquid water on the surface, it's not so far away from the sun that it's frozen over because it doesn't have any air pressure. It doesn't have any atmosphere to hold that liquid water in liquid form. It will just evaporate because you need the pressure as well as the correct temperature. And then we talked about that energy, how matter absorbs energy and emits it in the spectroscopy form. So that's what we're going to be carrying on with now. So this was that picture of the atom that we talked about. Oh, and if it's your first time here, we're streaming this live, and we will do this class for about half an hour, and then once we're done with the lecture, I will close the recording. If you're watching it after the effect, that's all you get to see, and then we will kind of hang out and just chat. All right, so the Bohr model of the atom, that's this idea that you have the nucleus at the center, you have these electrons going around in shells, and then they can jump energy levels, which is what we see here. So going up very distinct energy levels, and that's really the important thing, that when you do get an electron dropping down, it emits a photon, but because it's dropping from a distinct energy level to another distinct energy level, that energy difference corresponds to the photon, the light particle that gets released. So it's at a very specific frequency. And that's what we can see here. So, imagine your nucleus is down here at the bottom, and then these are the energy levels that are surrounding it. These are the different orbits. You have this, base, we'll just say, for example, the n equals 2 energy level. Then we have 3, 4, 5, and 6. When this atom gets heated up, that energy is going to be absorbed, and the electron's going to jump up a level. And then it will lose that energy. And based on where it falls down to, which excited state it jumped to and where it falls down, that's going to correspond to a specific energy. And then that can be translated to a specific wavelength, because it's the energy and frequency is tied together, as we found out from the photoelectric effect. So because of this, we can learn a lot about space. And this indeed is how most astronomy is done, is by studying these electrons dropping or absorbing as we go through. So remember, we talked about the different types of spectra that we have out there. One is a continuous spectra. So this is when you have a high density hot matter. A star is a good example of this. You can run that light that you get from that star through a prism, and you get this nice continuous spectrum. And we'll look at a full spectrum as well, but using the visual light for now really helps. You could have a hot gas. So maybe it's not a high density. Maybe it doesn't contain a bunch of stuff that's all just clumped together. Maybe it's just hot, 1 or 2 elements. They're going to be giving off that light because it's, the electrons are constantly dropping down. They heat up, they drop down, and they give off these very specific frequencies. These are each energy level that electron is dropping down from. Or you could have a high density hot matter and then a cold gas in between that. When that cold gas absorbs that heat from this source, it bumps those electrons up energy levels, and then when they drop back down, those photons go off in random directions. And so when we're looking right down this path, we see these gaps based on where they took that and then dropped. So those are the main kind of spectra that we use in astronomy. Now here's another visualization of it. This is a little bit more astronomy-wise and combines it all together. But again, this is just comparing your line of sight. So you have this source of a continuous spectrum. If you're just staring directly at that, you're going to see this nice rainbow, this big continuous spectrum here. If there's a cloud of gas in between, if you're just staring at the cloud of gas itself without the star anywhere in your line of sight, you're going to see just the emission lines that are coming from that cloud of gas. But if you're staring down the barrel of having this star behind the cloud of gas, you're going to see both this continuous spectrum, and then you're going to see these absorption lines. And remember, it's not because this cloud of gas isn't emitting those lines. It's because it absorbs all that light coming from this direction, and then when it emits that frequency, it throws it out in random directions. So you see these as gaps when you're looking down that line of sight with a hot source in the background. I hope that makes sense. It takes a little while to wrap your brain around, which is why I've explained it a few different ways now. But I can appreciate that it can be confusing, and it did take me a little while to figure that out. Christoph, thank you. So I was talking about, here, this is, we're saying kind of a neutral gas, kind of neither hot nor cold. But if we're looking back at this example, we're talking about it being a hot gas or being a cold gas. And then as the light passes, that light is carrying energy. That energy will transfer to those particles as heat, but that heat will excite that electron. When that electron drops down, it will lose that energy. So we are going through energy transfer processes where we're saying, kinetic energy is that heat, that vibration, but that vibration bounces up those electrons and then it loses that energy as light again. I hope that makes sense. It's really that for example, maybe I'll use this example and this will help a little bit. It's easy to see hot clouds of gas in space because whether or not there's a star or a light source behind them, you can see, yes, I am talking about spectroscopy, whether or not you can see a source behind them, if you just have a hot cloud of gas, it's going to be emitting a spectrum that looks like this. Because it's hot, just on its own, maybe it's close together, the particles are moving quickly, it has high amounts of energy in its own right, so we call it hot. It's going to be emitting a spectrum that looks like this. Cold clouds are much harder to see because they're not going to naturally be giving off this spectrum. Their electrons aren't going to be excited because there's no energy there from that heat. And so the only way you can see cold clouds of gas in space is if you have an energy source behind it. This was one of my first research that I did in astronomy was trying to find cold clouds of hydrogen gas. And what we did is we looked at the spectra out in space, just like this broad field of, space radio astronomy. We just took in all this spectra and we did a filter to see if there were any dips in that spectrum. If we found a dip in there, what we did is we looked then at that specific region to see if there was a bright source of light behind it that meant that something was getting absorbed in between. So I hope that makes sense. But yeah, that's just one example of how this gets applied. Here's another way of showing it. Again, I don't mean to drill this all the way home, but it's really helpful. Also, if any of you remember being in a physics or chemistry class and you were given tubes and you were told to take the diffraction grading of it, that was this. To try to figure out what all of those elements are. But here's another example. This is all hydrogen. That Balmer series, that's in the visible range, but I'm using this picture to also show that it's not just visible emission or absorption lines. You also have these throughout the entire electromagnetic spectrum. Oh, thanks for the follow. So, like I said, if you did this in chemistry classes, this may be coming back to you. This is what you were doing. You didn't just show up and you had cool tubes of gas that you had to very carefully insert into a heating element and then look through glasses and try to identify what those were. You were doing spectroscopy. And so those tubes of gas that you were trying to figure out what they were. They weren't labeled. You would see these lines and then you had to try to figure out what element you were looking at. What that was it was just a tube of, and if you didn't do it, here's an example of it. You get a tube of gas. It doesn't have any light. You can't see what it is. You don't know what it is. There's no label on it. What you do is then you insert that tube and you basically run a current through it. So you heat it up. It's like plugging in a wire in a toaster. You're just heating up that gas. When that gas is heating up, what that does is those electrons are jumping up and then they're falling back down at very specific frequencies. If you remember this, when you looked at them, maybe that tube was glowing like kind of red or kind of purple, but you couldn't really differentiate what it was doing until you looked at it through a diffraction grating. What that diffraction grating was just a prism. All it did was it just separated this whole frequency, and then you were able to differentiate these lines and identify these elements from there. But like I said, even though this is a really easy lab that a lot of people have done maybe in high school, this is spectroscopy. This is what astronomers do all the time. It's just we don't get to look at it like cool like this. We have to actually look at the lines, which actually look kind of like this. I couldn't not put in the spectroscopy for Mass Effect. So this is a video game. This is not astronomy. But when you play Mass Effect 2, you scan planets. And what you do when you scan the planets is you've hovered around it and thank you. And now how you're necessarily doing this, we don't have to get into the details for, and why it's only these 4 specific elements, we don't have to get into the details for. That's all the science fiction side. But what I really like is you just have like a neutral spectrum there, and then you see these emission lines. These emission lines are showing you that there's something there in that specific element. So you launch a probe and then you absorb it. In what situations would falling to a lower energy level not emit a photon in that cold gas cloud? Becca, that's a really good question. And The answer is that there isn't any situation where falling to a lower energy level would not emit a photon. A cold gas cloud, so there's a couple things here. If you have a cold gas cloud, that means those electrons are all in their lowest state. Because it's cold, there's no energy there. So this is just that conservation of energy idea. So they're cold, there's no energy there, so they're all in their lowest state. If there's any residual heat, any random thing that comes by, an electron may get excited, it may go up to a higher state and then fall down. It is always going to emit a photon, but the key is we may not see it because it may go off in a direction that's not in our line of sight. So it could take off in another direction and then we wouldn't see it. But it's still emitting a photon. It's still dropping an energy level. It's just dropping. That photon will then go off in a direction that we don't see. So we don't see that line then. I hope that makes sense. So you still might have like a cold gas that does have some heat in there, but we're just not able to see it because of all those random directions. It just has to be in the direction that we're looking. Awesome. All right. So that's drilling home spectroscopy. Now we're going to get into thermal radiation because remember when I showed that continuous spectra? Yeah, okay, when there's light heat behind it. Yeah, it will always get excited. It will always drop down. It will always emit a photon. It just has to be in that line of sight for us to see it. And because it's usually not in our line of sight, that's why we see it as a gap. Cool. But this is now getting into why we have the continuous spectra and what it actually looks like. What I showed going back here as a continuous spectra, we were just showing a rainbow. But what it actually is it crosses this whole electromagnetic spectrum. So this is the example of a couple of stars here. And so what we see is, this peak, this rainbow. If you take sunlight, take a prism, it's going to do that, and you're going to see a rainbow. So that's the continuous spectra. But there's little nuances here that we have to deal with. Now, I apologize ahead of time. This screws up all physics students for all time, forever and ever, because wavelength and frequency are different. So if you notice, some of my spectra are going from red up to purple, and we go low energy to high energy. This is going from high energy to low energy because we're measuring wavelength. I can do nothing but apologize and offer a challenge to people to try to find a consistent use when you're trawling the internet for images that you can use in your lecture. Because it's just a nightmare. All I can do is just point it out every single time. So this is where we have low energy. This is where we have high energy. But this is that continuous spectra. When you have a source of heat, you're giving off radiation. So this is what we call thermal radiation. Now, whether it's visible or not is very different. You can see all of these stars here cross through the visible spectra. That means that we can see them with our eyes. Now, you don't want to stare directly at the sun, obviously, but the fact that you can see the sun shows that its thermal radiation crosses through our visible spectrum. Now, humans reflect light. There has to be a light source for them to reflect. If you're in a super, super dark room and there's no light source anywhere, you can't see the other humans in the room with you. They're not naturally giving off light in the visible spectrum. That would be super creepy. But our heat, our temperature, this is measured in Kelvin. So this is, a healthy about 198-ish degrees for a human. But a human gives off thermal spectra. We have heat. We have natural heat. But because of where our temperature falls, we give off light in the infrared. So if you played with infrared cameras, night vision goggles, all of that stuff spill into the infrared. And so if you're in a dark room, you have heat vision. Heat vision goggles. If you're in a dark room, you have heat vision. Then you're able to see the other humans in there with you because we're giving off light in the electromagnetic spectrum. We're just giving it off in the infrared part. That's why Predator is scary because Predator can see in the infrared. So super fun to play with. And the next time you are able to step foot into a science museum and have an infrared camera, those are very fun to play with. Good. I'm glad you understand. there's a couple of laws here that you can see visually, but we haven't gone through distinctly yet. But there are two laws of thermal radiation, and we'll use this chart to talk about them. The first one is the Stefan-Boltzmann law. What that says is every area of a hotter object is emitting more light. That's a very kind of complicated way to just say that, all right, this blue star is hotter than this yellow star, and so at every part of this whole spectrum, it's giving off more. So if you kind of put a line here, it's giving off more, because it's hotter object. So even way down here, it's still giving off more light, more intensity, more light across all the wavelengths. At no point does it cross over and give less light than a cooler star. That's the Stefan-Boltzmann law. Wien's law, pronounced Wien, Wien's law says that hotter objects emit photons with a higher average energy or shorter wavelengths. So that's saying that this peak here is going to be a higher energy. So that's looking at specifically the peaks of each of these objects. So the hotter objects are going to have a higher average energy. Remember, this chart is backwards. The lower part here is a higher energy. This is where purple is. This is going up into infrared, and then X-ray, and then gamma, or not infrared, sorry, ultraviolet. See? All right. This is the higher energy. You get past purple, you go up to ultraviolet, then you go into X-ray, then you go into gamma ray. So higher energies are on this side. Hotter objects have the higher average energy. Their peak has higher energy than cooler objects. So the first law just says that across the whole spectrum, hotter objects are always going to be giving off more light. The second law is saying that hotter objects are going to peak at higher energies. So you're looking at where that peak is. And the cool thing with this is that this kind of shows why hotter stars are bluer and then cooler stars are redder. That's because that's where their peak is falling. And that's what you can see here, is that we have a star that's about 3,000 Kelvin. Its peak is going to be in the redder. There's going to be a little bit more energy in the red area, and then it's going to be giving off hardly any energy in comparison in the other frequencies. So if you're just looking at this specifically, you can see its intensity is greater in the red part than it is in the purple part. Yeah, it is the opposite of Roy G. Roy G. Biv is going that way. And my thing is mirrored, so I'm a hot mess right now. Hot mess, see? So yeah, you can see that the intensity, the brightness here for a cooler star is going to be redder, more red, than it is purple. So the cooler stars appear red. Our star, the sun, kind of lies perfectly across here, but technically the peak is in the yellow greenish area. That's where the highest intensity is. So that's why our star appears yellowy greenish. And then these really, really bright stars, even though they peak further down in the ultraviolet or X-ray range, their intensity in the visible spectrum, their highest intensity is in the blue-purple area. So that's why these stars appear to be different colors. It's based on their temperatures. And if we can see the color that they are, we can figure out what the temperature is based on these laws, which is super useful and what we do in astronomy. Another way to visualize this, blacksmithing. So sticking pokers into fires. When you have just a rod of metal on its own, it's not giving off any light. Again, think about it. If you were in a really dark room, you wouldn't be able to see it because it's not emitting any light on its own. As you start to heat it up, you're increasing its temperature. It's going to start glowing red, such that in a dark room, you would see it glow red. And then it would start to get brighter and brighter and brighter as its temperature increased. And it's giving off both higher energy, higher intensity, as well as higher energy. So it's giving off brighter light as it's going. How or where in the EM spectrum does light turn into radio waves, and do they cross over in a large portion? That's a good question. So I'll pull up because I don't have the spectrum in this slide deck, but I can pull it up afterwards. But if you're watching this after the fact in week 7, you can go have a look at it. But light we can, however, look at this here. Okay, so how or where in the EM spectrum does light turn into radio waves? Light is always going to be radio waves. It's just really long wavelengths. So radio waves are going to be way, way, way over here. And there are objects in space that glow in radio waves. They're just very cold. So we have, humans down here is in infrared. Over here is radio. So you will have things that show up and that peak in the radio part of the electromagnetic spectrum. They're just very long wavelengths, very low energy, very colder, effectively, objects. So, for example, hydrogen clouds, they're very prominent in space, but they don't have a ton of energy compared to some of the, atoms that have much higher energy levels. So there's going to be a lot of radio signatures there. Now, thinking about radio, when we hear the term radio, we think sound, because sound comes out of our radios. So thanks, English, for doing that to us. All that's doing is it's a very confusing way of saying that we transmit radio signals, electromagnetic radio waves travel very nicely around Earth because they have these long wavelengths. They're able to bounce off the atmosphere. They're able to travel very far because they, just because of the structure of them. And then radio antennas pick up those essentially they're such long wavelengths that you have your radio antenna is just picking up this radio wave and then translating it into sound. So it's carrying information in the radio part of the spectra. I hope that makes sense. I know it's very, very confusing. But talking about your questions specifically with radio waves in the electromagnetic spectrum, they are light and they're just very low energy, so they appear down here. So colder objects will peak in the radio spectrum. Good question. Thank you. The blacksmithing, this is sort of that intuitive thing. And again, we learned that fire is red, but also worse fire is blue. When you start to look at a candle, it's red on the outside and then it gets bluer as you're getting closer because that's where the hotter part is. It's still hot in the red part, but blue is actually hotter than red. And this is why. Law of thermal radiation. Okay. So using this in astronomy, this is a great image. And if we were taking this class, I would definitely put this on homework, if not an exam, because this is awesome. So this is sort of a cartoony spectrum of Mars. What this is showing, there's a lot of information here, and this is why astronomy is used all the time. So remember, Mars will have its own heat because it's absorbing energy from the sun. But it's also reflecting light from the sun as well. So we're seeing both of those things here. This is the sunlight. This is, if you were to sort of take a solar, the continuous spectrum from the sun and plop it on here, remember it peaks in about the greenish yellow area. This is what the sun's looks like on its own because it's then hitting Mars, reflecting off. You're losing some of that intensity because some of that energy is being absorbed by Mars. But what's reflected off basically depends on what the surface is made out of. You can see that Mars absorbs a lot of the blue light, again, just because of what the surface is made out of, and it reflects a lot of the red light. That's why Mars appears red, just because of the material on the surface of Mars. So this is the sunlight hitting Mars, getting absorbed and then reflected. You can see it's got absorption bands here, so it's not this continuous spectra. We're missing some of the light that's coming back off because of carbon dioxide in the atmosphere. Doesn't make it through. It goes through, it gets absorbed. That light gets radiated off in different directions, so we have these absorption lines. And then way down here, that's the heat itself. That's Mars having its own thermal energy that it's absorbed from the sun and giving off as heat, not reflecting the visual light, but giving off as heat. And that tells us what its surface temperature is, what it itself's temperature is. And it's way down in the infrared. It's about 225 Kelvin. So that's how we can tell what temperature the planet itself is because of what its thermal radiation, what its continuous spectrum looks like. Remember, like humans are sort of here-ish. So Mars is slightly colder than a human, which makes sense. And then we still have some absorption lines here because of the atmosphere. And what's cool too is over here in the ultraviolet, there's actually some emission lines. That shows us that there's some heat in the atmosphere itself, and it's emitting in the ultraviolet, which shows that we have a hot upper atmosphere, that there's a lot of high energy up in the upper atmosphere that's giving off emission lines. So these are all the things that we can learn about Mars just by looking at its spectra and saying, okay, without even looking at a picture of it, we can say that it's going to look red in our visible spectrum. It's got some heat to it. It's absorbing some light, and then it's it's emitting that as heat. And that's in the infrared. How far away from our solar system can you see a spectrum from Mars with current technology? Ooh, that's a really good question. So, depends on the telescope. With our current technology, this is the cusp of exoplanet studies where we're at right now. And when we get to exoplanets, we'll talk a little bit more about it. But these studies have been, yeah, for sure. So this is the exoplanet idea. That's what these studies have been trying to look at, is trying to figure out how to make our telescopes better. So when we see a planet pass in front of a sun, if we can get any emission or absorption spectra to tell us what that atmosphere looks like. It's not impossible, and I know that we're trying to do it, but I think our telescopes are just not good enough. I know there was some look at we did have a visible telescope, and I'm sorry, I don't remember all this off the top of my head. We have a visible telescope that if there was an Earth-like planet within, I think, 5 light years, they would be able to see blue versus brownish as Earth turned. So if it was that far away from us looking back at Earth, you would be able to see a change in the visible spectrum, but maybe not to do specific spectroscopy. So how do we know what part of Mars' temperature is the sun? What's due to heat from the planet's core? We don't. That's defining the two. We know how much heat is given off, but we can kind of infer a lot based on how much energy is being absorbed from the sun, because we know the sun is sending this much energy to Mars, and then we could say how much energy is giving back off versus how much intrinsic energy it is itself. So we can kind of subtract the solar energy to figure out how much energy is part of, like you said, is internal versus external. But basically, once the sun hits it, it's going to be absorbed, and then internal or external, it doesn't really matter at that point. It's all being given off as thermal emission because it's absorbing that energy, and it itself becomes a black body. We have this continuous spectrum here. But like I said, you can subtract the energy from the sun to be able to get that. So yeah, they can't see exoplanets, but being able to differentiate and I feel like we have been able to do spectroscopy and see oxygen lines, or at least look for oxygen lines, but maybe that's just wishful thinking on my part. I don't know for sure, so I don't want to say definitively one way or the other. How many different kinds of telescopes do you need to get readings to make a spectra like this? That's a great question, and exactly our topic for next week. So thank you for that question. We will be talking about telescopes and telescope technology and how we actually get these spectra from different objects, because it's awesome. Okay, the last thing we're going to talk about, the Doppler effect. I would play this clip if I wasn't putting this online, but Doppler effect is going... The Big Bang Theory had some gems in the first few seasons. From a physics perspective, they had some gems. One of my favorite scenes is when Sheldon dressed up like the Doppler effect and just went around going, "Choo!" to everyone. So I would play that clip if it wasn't for copyright infringement, so you could just see the picture instead. But what the Doppler effect is exactly that. It's this idea that as a noisy object approaches us, passes us, we hear an increase in the frequency and then a decrease in the frequency. You hear it go, and what that's doing is it's increasing and then decreasing as it passes you. The Doppler effect is just showing that waves get compressed as they're traveling towards an object, and they get stretched out as they travel away from an object. A way I like to demonstrate the Doppler effect is to imagine that you have a spring between two friends, or a slinky. Slinky is probably a better example. If you have a slinky that you're holding straight between two friends, if you get closer to each other, and imagine it's on a flat surface, so it's not going to droop. It's flat. But as you get closer to each other, the springs, or the rings in the slinky, are going to get closer together. As you walk away from your friend, they're going to stretch further apart. So if you're treating sound waves or wave as, as light as a wave, it's going to do this regardless. So this Doppler effect is just the change in wavelengths due to motion towards or away from an observer. That's the definition. The change in wavelengths due to the motion towards or away from an observer, whether that's sound or light. But we can hear this and we can see it. So typically, the whole zoom, that's the sound example, because that's one that we're used to and we have heard. We just didn't necessarily think of it as the Doppler effect. But this happens with light all the time. And this is blue shift and red shift. So some of you may have heard of red shifting with respect to astronomy, or blue shifting, but may not have known where that comes from. It's just the Doppler effect. It's the effect from objects moving towards or away from each other. There's a great nerdy bumper sticker that astronomers get at conferences that basically says, it's a red sticker and it says, if you see this as blue, you're driving too fast. Dorky thing. But that's blue shift versus red shift. How we use it in astronomy is using this spectroscopy. So if an object is not moving towards or away from us, this is the spectrum that we would see. If it's moving away from us, it's red shifted. And if it's moving towards us, it's blue shifted. Now, the key here is, like, if we look at this line, for example, this last line down here, when we say it's red shifted, it's still purple. It still hasn't turned red. The point is that it's moved closer to the red side of the spectrum. And lazily and unfortunately, this even holds when you're past the red part of the spectrum. So if you're looking at infrared, if you're looking at microwaves, if they're shifting to longer wavelengths, we still say that it's red shifted. That's just the way that we use to confuse everyone. Because we're just using the visible spectrum as our reference point to say red equals long wavelength, blue equals short wavelength. So everything moving into longer wavelengths we say is red shifted, even if it's moving from red into infrared. So I'm sorry. And if it's moving, again, this line here that is in the red part of the spectrum, if it's moving towards us, it's going to be blue shifted. Doesn't mean it's turning blue. It's just moving to higher energy, shorter wavelengths. Sorry about that. There's nothing I can do to make that easier to understand. It's just the colloquialism. So just thinking red, longer wavelengths, blue, shorter wavelengths. And that reference point of just, if you're sitting in a test and you say, okay, if something is moving, if something is red shifted, that means longer wavelengths, because red is on the longer wavelength part of the visible spectrum. It's just how we remember it. And thank you, Valencia. The Doppler effect was named after Christian Doppler, Austrian physicist. Thank you. So yeah, this Doppler shifting, again, used in astronomy all the time. But the key is it has to be moving directly towards or away from you. So I can't believe I managed to make this look somewhat professional. This is a star that is moving directly away from us. We are going to see it red shifted, and that red shift is going to correspond exactly to its velocity. This star here, even though it's moving, we would not see its motion because of Doppler shift, because it's exactly perpendicular to us. So again, think about your friend and the slinky. If you've got that slinky between you two and you're walking there's a way you could be walking such that you're moving, but the distance between the slinky peaks is not changing. Now, it would kind of be a radial thing. But here is that example where if you're just walking along a table from your friend like that, it is going to stretch because there's some component that's away from you and some component that's perpendicular from you. So you're only going to see a slight amount of stretching. Sorry, I'm trying to do it. You're only going to see a slight amount of stretching from it moving away from you. Even though it might be hustling in this direction, you're still only seeing that small fraction that's actually stretching, that's actually redshifting. So we can't use this as like an end-all be-all to measure motion of objects in space, but we can use it as an overall clue. And when you're looking at the universe as a whole, when you're looking at sort of the big picture side, the universe is expanding, as you know, as Hubble found out. That means that as you start to get away from our little local area, once you start to get away from our galaxy and our local group, remember, going back to day one, if you're getting away from our local group and you're looking at galaxies and galaxy clusters as a whole, they're all redshifted. So that's kind of the key to realize everything's moving away from us and everything's moving away from each other. But really, like I said, this is Astronomy 101. I'm not trying to teach all of astronomy in one class. We're just focusing on the Doppler shift. So don't get too hung up about the expansion of the universe, the motion of stars. This is just stuff that we're going to be coming back to and referencing as we continue to learn about this stuff. Now, Doppler shift doesn't necessarily just have to be the motion of stars through our galaxy. It can also be looking at the rotation of stars. So we can figure out rotation rates based on how quickly a star is rotating. So a star that's not rotating is going to have just, let's say, for example, a specific line. Oh, thank you, Uncle Bill. But if it's rotating, that means some part is going to be blue shifted, some part of the star is going to be red shifted, and that spectrum is just going to be broadened out a little bit. So we can see what a spectrum for this star would look like at rest, and then we can see what that star looks like as we've observed it. And if it's stretched out a little bit, we can measure how quickly that star is rotating based on that, which is pretty cool. Do you have to have a stationary reading to compare with to know which way an object is moving? Yes. But thankfully, once we get into stars and learn about the HR diagram, you'll see that only a few things we have to learn about a star, such as its temperature, and then the different lines that we get from that star, we can then reference stationary versions of those things in order to figure out which way an object is moving. But that's a really good question. So we have these reference points that we can go back to. We're not totally blind. But again, this just goes back to how difficult astronomy is. It's this back and forth of being like, okay, I'm getting this spectrum from this object. I know that I can see the hydrogen lines in it because I have hydrogen gas here on Earth I can compare it to. So what's missing? And then starting to put all of those pieces together. Yeah, Andrew, we don't have to care about it now. But I'm glad they help. I'm glad this is useful. And then, you know, as Becca already asked, hey, Uncle Bill, this is a preview for exoplanets. We will be doing a whole class, if not two, on exoplanets themselves. But how we detect exoplanets, part of that has to do with a star's wobble. So this is just, there are multiple ways to detect exoplanets, but using Doppler shift is one of those ways. As a planet that we can't see, we can't observe, haven't observed it, is going around a star, as it goes around, it's going to be tugging on the star, right? When it's on this side of the star, it's going to be pulling the star a little bit towards us. When it's on this side of the star, it's going to be pulling the star a little bit away, so the star wobbles slightly. From that wobble, we can pick up the Doppler shift, and we can say there's something there tugging on this star. There must be a planet there. And to get ahead of maybe what some people are asking, yes, our star does wobble. It does not wobble enough like this. It doesn't move out of its own center of gravity. Its center of gravity stays within itself, but it does wobble enough that there is slight Doppler shifting, but there's a lot of planets, so it's also very confusing. But that's just a preview. We will be talking about this when we get to exoplanets, and it's exciting and fun, but the fundamental principle is Doppler shift. So that's why we got to drive that home. All right, so talked about spectroscopy, talked about thermal radiation, we talked about Doppler shifting. It's all come together hopefully nicely. Hopefully it makes sense. And like I said, now we're into that realm where it's like we've laid the groundwork talking about matter, talking about light. Oh, thank you for the follow. But we're now going to be using these constantly, especially these three terms: spectroscopy, thermal radiation, and Doppler shift. We're going to be coming back to a lot. So feel free to bookmark this, save it, come back to it. If maybe watch it a couple times. That's why we saved this. Because I don't have office hours other than being on Twitter a lot. But hopefully this can help start to make sense. So with that, if you're watching the recording, I'm going to end it here. Thank you for watching this. Feel free to like and subscribe and do all those things. And you can find links down below. We stream this at 1 o'clock Pacific time on Fridays on my Twitch channel, of which there is a link down below as well. So thank you for watching. If you have any questions, feel free to drop those in the comments, and we will catch you next time. Thanks.